So in this video, what we'll do is just review composite functions. So we'll start with this old SAC problem here. So we've got a linear function here and a square root function here, and I need to explain with working why the composite function g of f of x exists. Now remember that they use this notation, or this notation it's always been around, but they've put a stronger emphasis on this year, so worth noting that they may ask it like this. Now let's just do a quick sketch of them so we can see that this is linear. Its domain is 1 to 10. If we pop 1 in, we get 4 out. That's going to be closed. If we pop 10 in, we get 31 out. So 10 and 31, obviously not to scale, like that. So that's that function there. Now this one is the standard square root function, move 2 to the left, which matches its domain. Alright, so the best way to do, or to check whether the composite function exists, is to draw up a quick table. So I'm going to draw f of x, g of x, and include the domain and the range. So the domain of f of x is, as we can see, 1 to 10. And its range, we can read off that the lowest value it can produce is 4, and it can produce that one. It can go all the way up to 31, not inclusive. Now this one has a domain of -2 to positive infinity. And what can it produce? 0 to positive infinity. Okay. So basically, to form a composite function, what f of x can produce, i.e. the range of f of x, has to be a subset of g of x. That is, it has to be within the domain. So you imagine you give f of x values, okay, and it sends out y values. Now the y values it produces has to be a part of what g of x can accept. If it can produce an outer domain value for g, then the composition won't exist. Alright, so let's just check that. So we're going to say the range of f of x, which is 4, 31, and we're going to check whether it's a subset or not of the domain of g of x, which is -2 to positive infinity. Now that definitely fits into that, okay? Now sort of stuffed up a little bit there. I'll just say range of f of x is a subset of the domain of g of x. So I got a bit excited there and just wrote the domain straight in, okay? So this is actually true. And actually, if you want to show that the composition, just say the composition didn't exist, all you do is you put a slash through that just to say that the domain of the range of this function here is not a subset of the domain of this, and that would be a reason why the composition wouldn't exist. So that's how you would do it on the flip side. Okay, determine h of x, where h of x is g of f of x, and state the domain of h of x. So this is the domain of the new function. Alright, so we're going to do g of f of x, where f of x is 3x plus 1. Alright, so that means that basically everywhere where we see this x, we're going to replace it with 3x plus 1. So we've got 3x plus 1 plus 2 equals root 3x plus 3. Alright, so, and the domain of h of x is simply going to be the domain of f of x. So whatever f of x will accept, the function will accept. So f of x domain is 1 to 10. So we're going to say where x is an element from 1 to 10, not inclusive. Okay, so these are the values that f of x will accept. It turns it into y values, and then g of x accept those y values and turns it into something else. But basically the domain is going to be whatever the inside function can accept. Alright, so yeah, that's just summarizing those definitions, GOF, or I've heard them called, and if it's written the other way around, FOG, okay, is f of g of x. Alright, so just watch out for that notation this year. Alright, let f of x equal e to the 2x and g of x equals that. Okay, so what we're going to do here is invert f of x. Right, so we're going to write, let's just write y. So we're going to go y equals e to the 2x, swap x and y. Now you should know that the inverse of an exponential is a log, right? So this has got to turn into a log somewhere along the line. X equals e to the 2y. We're going to switch to log form. Log e x equals 2y. Y equals half log e x. And what we need to do is we need to write it with the notation f negative 1 of x equals half log e x, where x is an element. Okay, so the domain of the inverse will be the range of the original. So e to the 2x goes like that. So its range is 0 to positive infinity, not including 0. So we're going to go, that is going to be the domain of the log, 0 to positive infinity. And that makes sense because when that's inverted, it'll become that. Okay, so domain will be 0 to positive infinity. Alrighty, so that's the first one done. Alright, let's do the next one, g negative 1 of x. So first thing to note is, what does this function look like? It's 1 over root x. So if you recall from 7a, that's just a kind of hyperbolic type function, rectangular hyperbola, with only this part defined. Okay, only that part there. So that's why its domain is only the real positives. It won't accept 0 because 1 over 0 is undefined, and in methods you can't square root the negative. So that's going to be the original function. Now, what it's going to do, I think, will it just end up being the same? Anyway, let's just see. All right, so we're going to go y equals 1 over root x. We're going to swap x and y. So we're going to go x equals 1 over root y. Root y equals 1 over x, and y equals 1 over x squared. Right, so it becomes like, I suppose, a truncus. Okay, so the right-hand part of the truncus. Okay, so let's use the proper notation. G negative 1 x equals 1 over x squared, where x is an element. So we just go back to the original function and think about what the range is going to be. So we can see that the range is 0 to positive infinity. So 0 to positive infinity is going to be the domain. All right. Fog. F of g of x. All right, so we're going to do f of, now g is this function here, which is 1 over root x. So that basically means that e to the 2x, 2 times 1 over root x, equals e to the 2 over root x. All right, where x is an element. Now, where's this going to be defined? Well, so the domain of this is just going to be the domain of this, so it's going to be real positives, and that sort of makes sense given the nature of the function. G of g. So that's g of 1 over root x, which is 1 over root x. Is that right? that'll do. Alright, so we've got 1 over, now the square root of 1 is simply 1, and the square root of the square root of x, so what we'll do is write that as x to the half. We'll rewrite that as x to the half, and what we're going to do is, that's the same as that to the half as well. This is 1 over x to the quarter. Now that's 1 divided by 1 over x to the quarter, which is 1 times x to the quarter over 1, which is x to the quarter. Alright, so g of g is simply that. Now what's its domain going to be? It's going to be the same as the inside, so it's where x is an element of all real positives. Alright, now we've got the inverse of f of g of x. So what was f of g of x? We did that one over here. E to the 2 over root x. So we're just going to write that down. F of g of x equals e to the 2 over root x. Alright, so we'll just go y equals e to the 2 over root x. Swap x and y. X equals e to the 2 over root y. Ooh, what's this going to look like? Okay, so obviously we're going to go to log form. Log e, x equals 2 over root y. Okay, now we're going to go root y equals 2 over log e x. Y equals 4 over log e x all squared. Okay, it doesn't really ask us for the domain, but let's just try it out anyway. So what does e to the 2 over root x look like? I don't know. Probably worth our while just sketching that one. So we've got e to the 2 over what is it? Control root x. Yeah, so I wonder what the lowest value it is. 2 over. I'm going to pause this and have a quick think. Okay, so I think I've got this. So if you imagine x getting extremely large, okay, let's just go 1,000,000. All right, we square root it, it's still going to be large. 2 over a large value will be very small, i.e. close to 0. And e to the 0 is 1. So what this is going to do, this is going to approach 1. All right, so this function here, okay, is going to go like that, and the asymptote is going to be at y equals 1. Okay, so we can see that the range is going to be from 1 to positive infinity, and that's going to be the domain of this. So we're going to go f o g negative 1 do I need an x on there? Not sure whether that notation is correct. Negative 1, the inverse of this. Nah, I'm not happy with that. So I'm just going to write it like this. I'm going to write f of g of x inverted equals 4 over log e x all squared, where x is an element from, what was it, 1 to positive infinity. Yeah, alright, that'll do. Yeah, tough one, that one. Okay, the last one, we need to invert g of f of x. So I think I need to work out g of f of x first. So I'm going to go g of, now f of x is e to the 2x. So that's going to be 1 over root. And we're going to put that on for x. Okay, so that's g of f of x. Now we need to invert this thing. Far out. Okay, 1 over e to the 2x, swap x and y. X equals 1 over root e to the 2y. Right, root e to the 2y equals 1 over x. E to the 2y equals 1 over x squared. Log e 1 over x squared equals 2y. Y equals a half log e 1 over x squared. Oh god, I've got to work out the domain of this thing as well. I think I'm going to skip that. So I'm going to conclude g of f of x inverted is half log e 1 over x squared. Alright, let's have a quick think. So I need to work out the domain of this, I need to work out the range of this. So this is 1 over e to the 2x. Now e to the 2x looks like this. Now when we square root that, it should look, so if we square root these values, then it should look pretty similar. And then if we go 1 over, okay, probably got to graph this one as well. 1 over control root e to the, what was it, 2x. Alright, what the hell does this look like? Alright. So we can see that, so we've got an asymptote, does that go below the axes? Right, so we can see, yeah, that it's asymptotic at y equals 0. So the range is going to be 0 to positive infinity, and that means the domain will be 0 to positive infinity also. Alright, bit of a doozy, that one. Okay, for the function that, so x to the 2/3. Alright, now let's graph this first of all and state whether f is either strictly increasing, decreasing, or neither. So let's go f of x. Let's just imagine f of x equals x to the 1/3. That's this. Now what we're going to do is raise it to the 2, which would take this part and make it positive, so that's going to be that. And then it's only true for real positives union 0, so it's only going to be this part here. All right, so we can see that f of x strictly increasing over x is an element from 0 to positive infinity. All right, let's invert this thing now. So y equals x to the 2/3, x equals y to the 2/3, y, so what I'm going to do is raise this to the 3/2, okay, and that will be 6/6, and raise that to the 3/2, so it's x to the 3/2. All right, now that function is going to be x to the half, so it's the root function, then all of these values cubed, okay, and I'm not sure whether it'll go like this, parabolic, or whether it'll just spike like that, but either way we can see that f -1 x strictly increasing over x is an element. Alright, so really good practice this exercise for inverses and composite functions and all of that stuff. Yeah, so in the next video, I'll look at sums and products of functions and addition of ordinates once more.